So let us look at how contaminants reach the Arctic region. The contaminants reach the Arctic region through long-range transportation by air, that it takes very few days, or rivers, which takes months and years, or the ocean currents, which takes several years. So through the air, what happens is the less pollutant compared to the total load in the polar soil, sediment and water. That means air transports much less of the pollutant to Arctic region. This may be due to high pressure system over Siberia, no clouds and precipitation, Arctic haze, lack of photochemical degradation, global transportation of gases and dry deposition. These are all the reasons these are all the ways by which the contaminants reach the Arctic region through air. Some of the contaminants, especially sulfur dioxide, sulfates, non-volatile metals and radionuclides that are in the form of minute particles or aerosols, they start from the source and travel through the north flowing winds. When they fall on the ground, they stay there. These are called as one-hop contaminants. So this is a very important term you have to remember. These particles can stay in the winter air, that is up to 20 to 30 days, or in the summer air 2 to 5 days, because in the winter air it is colder, so they stay longer in the air. Whereas in the summer, these are very hot, so they are blown away very quickly. And when we look at the land and rivers, direct runoff, water-soluble components will be carried to ocean unless they were degraded. So that means the pollutants actually, if they are degraded in the ocean, they never reach the Arctic region. But if they are not degraded in the rivers and similarly, the poor water-soluble contaminants normally absorb onto particles. So this is another way how the contaminants reach. So through absorption on the particle, the contaminants are transported to Arctic region, and snow accumulation and release, erosive forces of meltwater, flooding or some other ways by which the contaminants reach Arctic region. Let us look at how contaminants reach the Arctic region. See, the transport mechanism for water-soluble pollutants are different from the one where the poorly soluble materials stick to some particles and they are transported. So these two have a different type of mechanism. So the water-soluble pollutants generally do not stick to any particle because they are actually in solution. And when the seawater freezes, brine is expelled into the water along with the water-soluble component. That means the pollutant is also being released. Between the landfast ice and the permanent pack ice, offshore winds often lead to the formation of areas of open water. So this is what is called the open water, and these flaw leads are called as coastal polynyas. So these flaw leads along with the coast are important areas for the interchange of semi-volatile pollutants between water and air. So this is how some of the soluble materials are being transported. The next major one is the role of river ice and continental shelves in the transport of contaminants. So we first saw air, then we saw river and waterways. Now we will look at river ice and continental shelves. So the ice gathers pollutants from the atmosphere, that is from the top, and also from the river, from the bottom as the water freezes. So if you look at the ice has pollutants in both sides, top from the air, bottom from the ocean. If the entire water column in the river is super cooled, a sudden change in temperature or turbulence can lead to ice formation around the rocks and sediments on the bottom of the river. So this type of ice is called as anchor ice. When the supercooled water is unable to form a solid ice cover because the water is moving or flowing fast, then that leads to the formation of fossil ice or the slush. This slush can collect small particles in the water and incorporate them into the ice cover. So this is how the contaminants can be transported. And then when the ice with particles containing contaminants become part of the pack ice, pollutants may be transported by the drifting ice because the ice are being drifted by the ocean current. Moreover, melting at the surface, drainage and refreezing from the bottom will redistribute the contaminants carried by the ice. So that means there is a complete mix of contaminants from bottom to top when the ice melts or when it refreezes. Similarly, cryoconites are basically a powdery wind-blown dirt. These are basically small rock particle soot or microbes which are present on the surface of the ice, and these can be deposited and builds up on snow, glaciers and ice caps, and these are also type of pollutants. So let us look at the carrier and the contaminant, because we had been seeing that if the pollutants are poorly soluble or like particles, then how they will be transported. So we are going to look at the relationship between carriers and contaminants. If the particles are small they often have the highest concentration of the contaminants due to the larger relative surface area, and these settle less quickly than the coarser material. So that's the reason the carrier, if it is very small, they accumulate lots of pollutants. The smaller particles and organic carriers are often more effective at long-range transport and can significantly impact the distribution and bioavailability of contaminants in the Arctic system. That means since the particles are very slow, they are also transported to a larger distances. So the small size contaminants, small size particles carrying contaminant are the most problematic one. Let us look at the comparison between large particle and small particles. Some examples include dust and ice particles are very large one, whereas aerosol and fine dust are very small particles. The contaminants which can be transported by the large particle include heavy metals and persistent organic pollutants, whereas in the case of small metals, they are heavy metals, organic contaminants and POPs. So how the transportation distance happens for the large particle, because they only travel shorter distances and settles out atmosphere very quickly because they are very large in size. Whereas the small particles, they are very small, so they travel longer distances and remain suspended in the air for longer time. So if you look at the binding capacity of the larger particles, they have less effective at binding contaminants and settles faster, because they don't stay in the air for longer time. Whereas the small particles, they are very effective at binding because they stay in the air for longer time and they also transport contaminants to a larger distance. When we look at the interaction with the ice, the larger particles can be incorporated into ice and released upon melting, whereas the small particles are trapped inside the ice and they also be released when the ice melts. With respect to the sediment transport, large particles are less significant in long-range transport, whereas small particles are very significant because they can be carried over long distances. And when we look at the bioaccumulation, the larger particles are less likely to be absorbed by the organism. So these are somewhat less problematic one, whereas the small particles are more likely to be ingested and absorbed, leading to higher bioaccumulation. So these are all the comparison between the large particles and small particles. And if you look at the type of contaminants, what are all the different types which are reaching Arctic region? One is pollutant from the mines, which may be metals, copper, nickel, titanium, and we also have coal and numerous rare earth minerals are there. And metal processing facilities also release lots of contaminants. Military operations, scientific research, factories, oil and gas drilling, waste dumps and settlements. These are all the various types of contaminants which are reaching the Arctic region. And through air, chlorinated hydrocarbons, mainly pesticides, enter the atmosphere from the spray drift, evaporation, volatilization and wind erosion. Mainly the industrial organochlorines enter the atmosphere through incineration and volatilization. So there are different types of chlorinated hydrocarbons or pollutants entering the air. The other one is the heavy metals. The source of aerosol in the Arctic are the atmospheric emission from European and Central North America. These are having a long-range transport of air pollutant is the major contributor. And if you look at the radioactive contamination in the Arctic region, nuclear weapon testing at some places in the USSR and maybe the crashing of American B-52 bomber near Thule Air Base in Greenland are some of the areas where the contamination exists. Of course, there are also naturally occurring radioactive materials which exist, like uranium mining in the Arctic also releases radioactive contaminants. The next major pollutant is mercury. So mercury is basically transported to the Arctic region by atmosphere, oceans, rivers, where it adds to already existing contamination cycles in the Arctic water, soil, sediments, ice, plants and animals. Of course, wildfires also around the globe are also important re-emission pathway for mercury to the atmosphere. Basically the boreal forest also, when it undergoes wildfires, especially in the Arctic where north is 60 degree, that also leads to lots of mercury contamination. The main form of mercury that is transported via atmosphere is basically inorganic one. In the aquatic system, both the inorganic and organic mercury are transported. Especially in the biology, the organic one, which is the methyl mercury, is the most important problematic one. Of course, there is a Minamata Convention which talks about methyl mercury contamination in the ocean. What are the challenges we need to address? There is inconsistency between the trends of increasing mercury emissions and decreasing air mercury concentration observed at the Arctic monitoring site. So there is more contaminants being released, but we are monitoring only less. Here are the mercury in the terrestrial biosphere when we look at. This is not mainly pertaining to the Arctic region, but in the terrestrial region. So one is the atmospheric deposition, second one is interaction with the carbon cycle. The uptake pathways are basically soil organic matter takes up. This bonds to soil, mercury bonds to soil organic matter, or stomatal leaf uptake is also happening through the leaves. And the next one is root absorption, and these are all the three ways by which the mercury is being taken by plants. And translocation in the plants also, basically mercury can be translocated by phylum, and additional mercury transportation takes place by dead leaves, roots and steins. And what are the different pathways by which mercury can be released? One is the evasion into the atmosphere, that is after microbial decay or microbial decay frees mercury from the organic matter. Then reabsorption by plants and soil organic matter of the released mercury, or leaf stoma transpiration, fire, leaching into groundwater. These are all the major pathways by which mercury can be released. And how the climate change is affecting this? It affects both the mercury transport, mercury chemistry and mercury bioaccumulation. So when we talk about mercury transport, the melting of snow and ice, permafrost thaw increases the mercury transport from terrestrial catchment areas. This also increases the severity and the frequency of wildfires, adds mercury to the atmosphere. So these are all the ways by which mercury can be transported. And the climate change also leads to atmospheric mercury deposition and re-emission from surfaces. And when we look at the mercury chemistry, basically the change in the cryosphere alters the seasonal evasion or retention of inorganic mercury in the terrestrial and aquatic environment. So they persist for longer time. And when we look at the mercury bioaccumulation, basically the benthic and pelagic shift in diet can enhance mercury bioaccumulation in pelagic species. Similarly, the climate influences mercury concentration in biota. It also affects but it's very difficult to understand because this process is a very complex process. And of course, changing the food web interactions and body conditions affect mercury concentration in animals. So these are all the ways by which the climate change is affecting the mercury transportation. So what are the atmospheric chemistry and the phase transformation of mercury? Simplistically, what we can say is the total amount of mercury emission basically consists of three major components. One is the gaseous elemental mercury, another one is a gaseous oxidized mercury, the third one is particulate mercury. So these are all the three major types of mercury that exist. Although both oxidation and reduction can occur homogeneously and heterogeneously, with our current understanding, it is difficult to quantify how all these changes are happening. So that's the reason understanding mercury contamination is the biggest challenge all the scientists are currently facing. Here are the three major types what we discussed about. One is the gaseous elemental mercury, the second one is the gaseous oxidized mercury, the third one is particulate mercury. If you look at particulate mercury, it is not very problematic one. The most problematic one will be these elemental mercury as well as the oxidized mercury. So the gaseous mercury actually has a very long lifetime in the air, that is close to 1 year. And this can also be transported to a larger area, that means global scale. And this is basically, since it remains for longer time, actually it is slowly removed by deposition or transformation to other forms. So that's the reason this gaseous elemental mercury exists in the air for longer time. And in the case of oxidized mercury, it is actually highly reactive. Even though it stays a shorter duration in the air, because it is highly reactive, it actually stays for a shorter time, but its solubility in the water is also high, so that means it can be transported to various places very quickly. And this is the most problematic one. This contributes to local deposition and it impacts the ecosystem. So the solubilized mercury is the most problematic one, which affects the ecosystem. And here are the chemical reactions given. One is the gas phase oxidation of mercury occurs basically in two steps. First one is the decomposition of XHG. So here X plus Hg plus M leads to XHG dot radical plus M. where X is hydroxide, chloride or bromine radicals. This XHG radical can react with another radical to form XHGY. So here Y is NO2 or peroxide or alkyl peroxides, halogen oxides, etc. M can be any gas phase molecule. So these are all the two reactions that are happening. So the decomposition competes with the second one, that is the combination reaction. But when X is equal to hydroxide, the oxidation is affected severely. But when X is equal to bromine, that oxidation is not affected. It is moderate only. The bromine HG can actually undergo photolysis with the NO2 to produce BrHGO dot. The reactions are given here. And this BrHGO dot, that is the radical, gets converted to BrHgOH by abstraction of hydrogen atom from the alkane RH group. Here it is given. So this BrHgO dot radical can react with RH by hydrogen abstraction to give BrHgOH. So these are all the various radical reactions that are occurring in the mercury